Good evening, everyone. Welcome to the fourth session of problem solving for the course Structural Analysis 1. So today we'll be looking at the conjugate beam method and unit load method for frames. So this will help you solve assignment number 5. So let's quickly get started. I hope I'm audible. Let me start sharing my screen. The recording has started. So we were yeah, could anyone confirm that my voice is audible and the screen is visible?
Yes, sir.
Okay,
Yes, sir.
thank you. So in the last session, we were looking at how to compute the methods for computing deflections in beams. So today we will be continuing on that. So last time I mentioned what is an elastic curve. So let me go through it. So or let me do this. Yeah. So in the last session, I introduced to what are deflections. What do we call as the elastic curve? That is the line connecting the centroids of all these sections. We call that as the elastic curve. And then we saw two methods to compute the elastic curve of a beam subjected to some specified loading and boundary conditions. So those two methods were double integration methods and moment area theorems. And then, so this week we'll continue to look at the methods to compute the deflection of a beam, deflection and slope of a beam. We will also extend it to frames using the unit load method. And we will be first looking at the conjugate beam method, and then we'll look at the unit load method. So let us look at what is the conjugate beam method, because you're already aware of the unit load method. So conjugate beam. So let me just a quick refresh it. So we saw that there are 4 different methods. One is double integration. Second is moment area theorems. So what did we do in double integration? That will be useful now. So we have M by EI is the curvature which comes from the beam bending analysis, where the radius of curvature is rho and a moment M is applied. And from calculus, we have that this is approximately equal to d square v by dx square, where v is the transverse deflection. So using this, once we have determined m of x, if we integrate this 2 times with appropriate boundary conditions, we can evaluate the integration constants and we will get the elastic curve of the deflected beam. The other thing, the other method we saw was the moment area theorems. They are they are geometrical. The method does the same as the double integration, but in a geometrical form. So what did we say? If a given beam subjected to some loads and we are interested in finding the slope or deflection at a point. We don't have formulas directly for the slope and the deflection, but what we do have is the change in slope of a point with respect to the tangent drawn at another point. So if the beam deflects this way, and this is point A and this is point B, the change in the angle between the tangents drawn at two different points, which is this, that is given by the area between the M by EA area under the M by EA diagram between these 2 points. So suppose M by EA diagram is something like this. This is point A and point B. This area gives theta B with respect to A. And there are certain sign conventions that we have already looked at. What was the other theorem? The tangential deviation. That is, with respect to a tangent drawn here, how much is this away? This quantity we call as TB with respect to A. And what is TB with respect to A? TB with respect to A is moment of this area about the point B. So these were the two methods. One was by integration, by calculus, and the other was geometric. Now today we are going to look at a third method, which is change. So today we'll be looking at the third method, conjugate beam method, and unit load method. So you're already aware of the unit load method from the trusses. So if we had a plain truss, what did we do? Suppose there is a unit load. Suppose there is a load applied here, P, which is a real load, or some system of loads, P1, P2, and so on. What did we do? Suppose we wanted to find a deflection at the tip, say delta. What did we do? We took another truss. We took the same truss and applied a virtual load of 1 kilonewton here, or 1 units, virtual load of 1 units. Then what did we say? Using the principle of virtual work, we said that the work done by the virtual forces on the real displacements should be equal to the work done by the internal virtual forces on the real internal displacements. So what did we do? So the work done by the external virtual force on the real displacement delta. So that is 1 delta is equal to summation over all members. So say a member I. Let's call this member I. And suppose the internal force, the internal virtual force is Ni, and the internal virtual force here is capital Ni. What did we say? So capital, and what is the internal virtual displacement in this case? It is nothing but Ni by Li by Ai Ei. So this is the internal real displacements, and this is internal virtual force. So the work done by the external, these are virtual, and these are real. So this is what we did. The work done by the external virtual force on the real displacement at the load point is equal to the total work done by all the internal virtual forces on the internal real displacements. Now the extension to beams is fairly straightforward. Okay, so we are going to do exactly the same. Only thing is, instead of having it as a summation, since a beam is continuous, we'll have it as a integration. So what did we have? We had one. What is one? So one is the externally applied unit force. Suppose we let me draw a beam. We have some beam, and it is subjected to some load. So this is the real system. Now let us consider, and suppose we are interested in finding the deflection of this point. Say call it delta. So now we'll consider the virtual system. Apply a unit virtual force here. Now this deflects something like and yeah, it will deflect like this. And this will deflect something like this. So so this is virtual system. Now what are the internal forces in a beam? We have axial force, shear force, and a bending moment. But usually the axial deformation of a beam, so axial deformation what is that? NL by AE is much less than the bending deformation. So in common practice, beams are treated as axially rigid. And the second assumption that gets into this theory is so we also don't consider shear deformations. So if we use Euler-Bernoulli beam theory, what do we say? We say that plane sections remain plane. They remain perpendicular to the neutral axis. And suffer no change in length and length unchanged. So what does this mean? So when plane sections remain perpendicular to the neutral axis, it means that if initially we had a beam section like this, after deformation, it becomes something like this. However, the 90 degrees between the beam center axis and the cross section. So this is the cross section and this is the beam axis. So in this case also the 90 degrees is preserved. So it remains normal to the neutral axis. So what does it mean? Although there is a shear force acting here. So although there is a shear force acting here, say let us say, suppose we take a small section of the beam, and there is a shear force acting like this. And there is also a moment. This action of the shear force tends to distort the beam, small section of the beam like this. In that case, what will happen? This angle will change from 90 degrees to some other number. So there is a shear strain caused by the shear force. So that will do some internal work. But what is the assumption? If they remain perpendicular, although there is a shear force, it does not deform under shear. So it is rigid under shear as well. So this is subtle. It's not under the shear force of the entire beam. It doesn't mean the entire beam is rigid. It means that a cross section of the beam remains perpendicular to the neutral axis. So the shear force, the work done by the shear force in distorting the cross section, in distorting the beam is 0. So V does not do any work. N, we saw that it's actually rigid, so N does not do any work, because why they don't do any work? For work, we always need force acting on some displacement, but we have only a force. Since it doesn't deform, it's not shear deformable, it doesn't deform in shear. So V doesn't do any work, N doesn't do any work. So M is the only internal force that does some work. Now let us come to this. Suppose, as I said, suppose we have this beam, and we wish to find this deflection. So the virtual, so this is the virtual system. So the virtual force does some work on moving this through delta. And since I applied this 1 kilonewton downwards, we have to take delta as downwards. So 1 acting on delta is equal to summation over all the internal forces acting on all the internal virtual forces acting on internal virtual displacement. So what is the internal virtual displacement for a beam? Now we already saw that corresponding to this NVM, so there will also be virtual internal axial force N, virtual internal shear force V, and virtual internal bending moment small m. We have already seen that this doesn't do any work, this doesn't do any work. So we can drop it from both sides. So what is the only quantity that does work? M. What work does it do? So if we take a small infinitesimal section of the beam, okay, so at a distance x, okay, at a distance x, let us take a small section of the beam, which is let us take this small section dx. Now, if you draw an exaggerated view of this beam, there is bending moment m of x. There it will be m of x plus dx, but it's okay. To a first order approximation, you can treat it as constant. And this is dx. So over this length, what is the work done by the moment? So this is small m because it is the virtual system. And in the real system, what do we have? It deforms under this is the real moment capital M of x. And the beam rotates by, so here it is suppose this angle is theta, this angle would be theta plus d theta. So this angle would be d theta. So this will be d theta, something like that, d theta by 2, d theta by 2. So what is the work done by the moment on this? It will be small m at the section x multiplied by the small infinitesimal rotation, because moment will not act on displacements. What are conjugate quantities? Force will act on displacement to give some work, and moment will act on the rotations. That is how you, those are the conjugate quantities in which produce work. So this will act on d theta. But we already know that d theta is nothing but, so we know that 1 by rho is equal to m by E. So this is the real curvature, but what is the real curvature? Is d theta by dx. And this is the real bending moment. So you can write d theta as, this is summation over all dx. Okay, we'll see what it is. So you'll get m of x, capital M of x by EI into dx. So d theta is this. So d theta by dx is this. So d theta is m by EI dx. Now, when you take dx very small, the number of such sections will be very large. So what it converges to is this summation becomes an integral. So this becomes integral over the entire beam. So this is for just for so entire beam is split into small sections and then add them all up. So 0 to L m of x, which is the virtual bending moment in the beam, multiplied by the real infinitesimal deformation, which is capital M of x by EI dx. So that's it. If you want to determine the force, if you want to determine the displacement at some point in the structure, apply a unit virtual force at that structure in some assumed direction. If your assumed direction is correct, you'll get a positive answer. If your assumed direction is wrong, you will get a negative answer. In that case, you will have to reverse the direction after finding your answer. Then what is the step? You find the real bending moment diagram, divide it by EI to get the real curvature diagram. Now what is the work done by the virtual internal forces on the real displacements? It is virtual bending moment acting on the real rotations. So integrated over the entire beam, you will get your answer. Now suppose this is for finding. So this is given in a given beam. If you have to find the displacement, you do this. You do that. You do delta is equal to integral 0 to L m of x by EI dx. Now, if you're interested in finding the internal, if you are interested in finding the rotation at a point on the beam, okay? So suppose you have a beam. You have some beam, it's okay. It's indeterminate, but it's still okay. And if you're interested in finding at what angle does the tip rotate, so it will rotate some. It will take up some angle like this, which is say call it theta A. In that case, you apply a unit moment, right? Because the external moment can only act on theta A. So that acting on theta A, right hand side there is no change. Only thing is you need to find the internal virtual moments caused by this external moment, small, say 1. Acting on the real internal rotations. So these two summarizes the whatever is required for finding the displacements, deflections and rotations by using unit load method for beams. Now let's look at the second method, which is the conjugate beam method. Now let us see what is the motivation for this conjugate beam method. So there is a static system and a kinematic system. So what is the static system? You have a beam, it deflects, and at any point you can have the deflection v of x, small v of x, and the rotation theta of x. Now, how are these two related? We know that we know that theta of x is dv by dx, and we know the curvature 1 by rho is d theta by dx. But from the analysis, right? You take an infinitesimal section, using stress strain relations integrated over the section, you will get, so you'll have sigma xx. Sigma xx will be linearly varying with the depth. So once you do all of it, you know that this is equal to m by EA. So this will be rho. This will be rho. This will be m. And this dx, something like that. So these are kinematic relations. You have a deflection field V. The rotation is given by its first derivative. And the first derivative of the rotation with respect to x gives the curvature, which in turn is related to the moments as m of x by EM. So this is one system. We can also talk this statics of an infinitesimal element. So if we consider an infinitesimal element of the beam of length dx, what are the forces? One, you have the applied force. Let us take upward applied force as positive, W of x, and you have the shear force. So this convention is very important for the conjugate beam method. Left side, it is positive, and right side downwards is positive. And you have the bending moment, which is m of x. As usual, sagging moments are taken as positive. Now we can always expand it in Taylor series. So what you get is m of x plus dx is some m of x plus dm by dx and the higher order terms. Similarly, v of x plus dx is v of x plus dv by dx plus other higher order terms. Now, if you establish equilibrium, right? If you say sigma fy for the infinitesimal element is equal to 0, what you get is dv by dx. So dv by you'll get v of x minus v of x minus dv by dx plus w of x dx equal to 0. So dx cancels, v of x cancels. You'll get dv by dx is equal to w. And if you say sigma m is equal to 0 about any point, you will get v of x and v of x so you'll get a moment of v dx is equal to m. Again, there are higher order terms, but those can be neglected. So v dx is equal to dm by dx. So there's an m this side, there's an m this side. So m of x plus dx minus m of x is already there. That is the excess counterclockwise moment dm by dx. And what is the clockwise moment? Clockwise moment is v of x dx. So if you equate both, you get v dx is equal to dm by dx, which means v is equal to dm by dx. Now, if you summarize all these quantities, you get on the left hand side, you have not this. You have theta is equal to dv by dx and w is equal to d capital V by dx. And on this side, you have v is equal to dm by dx and the load intensity W is equal to dv by dx. Now, if you see, these two systems have the same, sorry, here it is. So here you have m 1 by rho. This is curvature is equal to d theta by dx, which is also the same as m by e. Now, if you see, these are mathematically identical. These two systems are mathematically identical. If you replace theta by v and yeah, so wherever you have theta, you have v on this side. And wherever you have v, the deflection v, you have moment on this side. So they are mathematically same. Mathematically identical systems. But the boundary conditions are different, because what is a boundary condition on displacement cannot be the same as the boundary condition on moment. So boundary conditions are different. So what we can do to determine if M is known, so you should be careful. So we already know that if W is given, if we know W, we can integrate once and get the shear force V. And if we know V, we can integrate once again to get the shear bending moment M. Here, same thing. If we know capital M, we can integrate once to get the slope theta. And if we know theta, we can integrate again to get the deflections V. That is what we do in the double integration method. But even without using double integration, if we are interested in getting the slope or deflection at a given point, this gives a shortcut. That is, in this case, what is W equivalent to? W is equivalent to the curvature. So the idea is this. Once we determine the internal forces M of x and V of x, construct a conjugate beam. Why? What is the fact that the way to determine the deflection is exactly the same as the way to determine the moments from a given loading. So the trick is to construct another beam, not the real beam, construct a conjugate beam with loading. Let us call this W bar or something as M by L. Then do a static analysis of this conjugate beam. So in this case, we have, so what do we get, right? From the similarity, from the mathematical similarity, what we get is, so the first theorem is slope at a point on the real beam is equal to the shear force at a corresponding point, at the corresponding point, because there's only one corresponding point in the conjugate beam. And the other thing, of course, is deflection at a point on the real beam is numerically equal to the bending moment at a corresponding point on the conjugate beam. So that's it. Now, given this, what are the boundary conditions? The boundary conditions are not the same. So how do you determine the boundary conditions? Just use this. The conjugate beam, the boundary conditions should be such that they respect the kinematic constraints in the real beam. So it is simple. Let us see. Suppose you have on the real beam, if you have a hinged or a pinned support, what does it mean? The deflections are 0 on the real beam. What does this mean? Suppose this is point A. The deflection at the point A is 0 and the rotations at the point A are not 0. So what does rotations correspond to in conjugate beam? Right? What does the rotations correspond to? They correspond to the shear force. Yeah, so they correspond to the shear force V on the conjugate beam is not 0 and the moments, this is A. So, and the moments are 0. So which type of boundary condition simulates this? It's the same thing. So here the shear force is non-zero. That's a vertical force, but the moments are 0. Now, if you have a free end on the real beam, what does it mean? So this is a free end. The deflections are non-zero. Rotations are also non-zero. So what does it correspond to? Moments on the conjugate beam. Let me put a bar here. Moments are non-zero, and the shear force is non-zero. So what does that correspond to? It's not a free end. It is a fixed end. And if you have a fixed end here, the deflections are 0 and the rotations are 0, which means on the conjugate beam, bending moment is 0 and the shear force is 0. What does that correspond to? It corresponds to a free end in the conjugate beam. So these are how the boundary conditions are related. So very simple. Given any beam, given a beam, find out its internal bending moment diagram. Now construct a conjugate beam with a loading equal to m by En, and then carry out a static analysis of the conjugate beam subjected to these boundary conditions, these transformed boundary conditions. Then you will get in one shot, you can get the deflections and the rotations at any given point in the real beam. Now let's go to the problems. So before that, in the last session, I made a mistake in this the solution to this. So we were let me clarify that before we go ahead. So what did we say? By symmetry, we said that the beam deflects like this, with the maximum deflection occurring in the middle. So if the maximum deflection occurs in the middle, the slope there should be 0. So the tangent drawn here will be like this. So let us call this point as C. Let us call this point as B. And let us call this point as D. Now, what was the question that is, so in this case, what is this? This is TB with respect to C. And this distance is TD with respect to C. Now, if you draw a horizontal line connecting these two, this will be delta C. And this will be, sorry, this, if you extend it here, this will be delta D. So what is that we know? We know that delta B is 0, delta C, right? Delta C plus delta D is equal to TD with respect to C. Well, the tangent is drawn here. This distance plus this distance will be equal to TD with respect to C. And what is delta C? Delta C is equal to TB with respect to C. Numerically, I don't consider the signs, so I can put a mod here. Numerical values are like this. Now let us find, so if you draw the bending moment diagram for this, looks something like this. At points, so it is very simple. At this point, what is the bending moment? Minus P into A, and this side it's the same. So connected by a straight line. So here it is minus PA minus minus minus. Now what is TB with respect to A? It is, yeah, another thing from these two, right? What do we get? We want to see at what A delta C is equal to delta D. which means TD, mod of TD with respect to C is 2 delta C, which is nothing but 2 times mod of TB with respect to C. So this is the condition we have. TD with respect to C is 2 times TB with respect to C. Let us see, first of all, see what TD with respect to C is. So TD with respect to C is the moment of this entire region above this point. So let us split it up into one rectangle and a triangle as it is. Okay. So what is the area of the rectangle? Area of the rectangle is minus PA into what is the distance it acts through? L minus 2A by 2. So this is L minus 2A and it is half of it. And where is its midpoint? So so this is the distance over which it acts, and where is its midpoint? It is here, which is L minus 2A by 2 by 2, which is L minus 2A by 4. So this distance is L minus 2A by 4 plus A. And yeah, that's it for the rectangle. And there is a part coming from the triangle, which is minus PA acting over A by A, and you need to take half. And then where is the centroid of this triangle? 2A by 3. So 2A by 3. So if you simplify it, you'll get minus PA into let me give the simplified expression. We'll get into today's thing quickly. You will get minus PA into L minus 2A the whole square by 8 plus A into L minus 2A by 2 plus A square by 3. Let's also find out TB with respect to C. So TB with respect to C is simple, minus PA, right? It is area of this, moment of the area of this about this point. So minus PA into L minus 2A by 2 acting at L minus 2A by 4. That's it. Now let us do, so if you take modulus, that's what we need. Mod of TD with respect to C is mod of TB with respect to C, 2 times mod of TB with respect to C. If you do that, we can make this plus plus. So PA on both sides will get cancelled. You get a quadratic equation, which is this. Let me write it down directly. We'll get minus 7 A square by 6 plus AL minus L square by 8 equal to 0. So this is the condition that should be satisfied for the deflections to be equal. Now, if you solve this, you'll get two roots. So one of them, so we'll say one of them is A is equal to 1.152 L, and the other root will be A is equal to 0.70 something L, 705 L or something. But this is not possible. So this is a unphysical. Why? A has to be less than L by 2. Otherwise, what will happen? These two supports will cross over each other, which means the right support is on the left and left support is, and L minus 2A will be a negative value. So that is absurd. So this is not physical. So this is not physical. So this is the right answer. So the answer is 0.152 L. Now let's go to this week's questions. They are very simple. So yeah. Usually we are given the loading and the support conditions, and we'll find out the bending moment diagram. So today we are going to do the reverse. The question that we look at today is the reverse of it. So we are given this bending moment diagram, and we are asked to guess the loading conditions. So yes, any guesses? It's very simple. Let us name the points A, B, and C. Yeah. So could anyone make a guess? It's simple. Out of these. Okay, fine. Yeah.
Last one.
Last one. Yes, that is correct. So let us see what is the reasoning for that. At A, what is the moment? At A, moment is 0, and yeah, moment is 0, and the slope is non-zero. So if the slope is non-zero, it means there is a shear force, and there is no, and the moment is 0. So what gives that? This kind of a support, hinged support, gives that condition. Okay. So at A, we have something like this. At B, what do we have? At B, the left side shear force, the left side slope is different. It is continuous. Moment is continuous, but the left side slope is different from right side slope. What does it mean? If there's a discontinuity in the shear force, it means there's a point load or a support. There's a point concentrated load acting there. So at B, we either have something like this or like this. So B is either something like this or like this. So one of these two is there. And what is the condition at C? At C, the shear force is 0. The slope is 0 here. See, the slope is 0, but the moment is not 0. So at C, we either have something like this, but this will resist a shear force as well. So you either have a guided roller or you have applied moment. And between A and B, how is the profile of the bending moment diagram? It is a parabola. So it is what results in a parabolic bending moment distribution? It should be a distributed load. It cannot be a point load. So between A and B, you have some uniformly distributed load. So if you put all these together, what is it? You get A at you have something like this, B either this or this. So let us take this. And in C, it is under pure bending. There's no shear force. So have a moment here. You don't have this. So if you put all these together, it corresponds to B. That's the right answer. Now, question 10 is also very similar. So let's do that. Again, this is, let's do the guesswork again. So anybody can guess? So let me zoom out a little bit so that you can. Yeah. So this is the given bending moment distribution. What do you think is the right answer? Again, let me name this A, B, C. Any guess? Okay, let's go through the same thing. At A, what do we
A.
have? Yes, that's correct. So VA is non-zero. Why? Slope is not 0. And moment at A is 0. So it is something like this at A. And between A and B, what do we have? We have something like this because there is parabolic bending moment distribution. At B, what do we have? At B, we either have a concentrated force or a support. So this is at B because the shear force is discontinuous, left and right. So at B, we have something like this. At B. And at C, what do we have? Same as A. So at C, we have a slope, which is shear force, and bending moment is 0. So at C also, we have something like this. So if you put them all together, this is what you will get. Between A and B, you have distributed force. At A, you have a hinge. At C, you have a hinge. And at B, you have an intermediate support. So this is what you will get. Now, let's go to the second question. Again, it's a simple question. So it is along the same lines as the last one. So this is a real beam. Again, let me call this point as A, B, C, and D. So what are the conditions? Let us list the conditions. What is the displacement at A? Yes, you can answer. 0. Rotation at A? 0. Correct. And then now what is the displacement at C? 0.
0.
Rotation at C?
Something.
Not 0.
Not 0.
And displacement at D? Not 0. Rotation at D is not 0. So these are clear. So yeah, what does this mean? So at A we have, so now this corresponds to the conjugate conditions. Let us look at the conjugate conditions. I'll come to the point B. We'll see very soon why I have postponed it. So what are the conjugate conditions? On the conjugate beam, the displacement is same as moment, which means the moment at point A on the conjugate beam is 0. Shear force on the conjugate beam at point A is 0. This means the moment at point C in the conjugate beam is 0. And the shear force on the conjugate beam at the point C is not 0. And here it means the moment is also not 0 and shear force is also not 0. D. Now let us look at point C. That is a bit interesting. So let us subject it to some loading. In that case, how does point B deform? On the left side, it is a hinge. So it does not transmit moments. So this side it is, how does the hinge work? You know, right? You put something like this, put two bars like this. This can rotate independent of these. So the angle on the left and right need not be the same. So here you can have some angle and here you can have a completely different angle. So the condition there is the displacement of the point B is not 0. That is clear. And the rotation of the point B on the left side is not the same as the rotation of the point B on the right side. Now let us transfer it to the conjugate beam and see what it corresponds to. So this means that the moment this means that the moment at point B on the conjugate beam is not 0, and the shear force to the left and the right of the point B on the conjugate beam are not the same. Okay, so the left side shear force and the right side shear force at the point B are not the same. What does this mean? So there's a jump in the shear force diagram. When does that happen? When there is a concentrated force or a support. So now let us draw the supports corresponding to each of them. So at A, what do we have? At A, what makes both shear force and bending moment as 0? It's a free end. So A should be a free end. And what about B? So left side we have some shear force, right side we have some other shear force, and the bending moment is not 0. So B means it means we have an intermediate support. Right? If there's an intermediate support, then there's a reaction force, concentrated reaction force, which creates a jump in the shear force. Left hand side and right hand side are not 0. But the bending moment will be non-zero and continuous. So it deforms something like this. So yeah, so at B we have something like this. What is the condition at C?
Internal
The
hinge.
shear force, internal hinge. Very good. Why? Moment is 0. So at C, the moment should be 0. And the shear force is non-zero. And not only that shear force is non-zero, shear force is also continuous. There is no, so it's not just enough to say there's an internal hinge. We should also say that there's an internal hinge and it doesn't have any concentrated force, right? If there's a concentrated force, even if it's an internal hinge, it will have a discontinuous shear force. So here the rotations are continuous. In the real beam, it will rotate as a single unit. So right side and left side, the rotations will be the same. Rotations are continuous, which means the shear force is continuous and it is non-zero. So what gives that? An internal hinge. That is correct. Good. And what do we have at D? Both the bending moment and shear force are non-zero. So you have a fixed built in it. Now just put them all together, right? So what do you get? You get, let me zoom out. If you put them all together, you get something like this: A, B, C, D. So what this is? It is this one, B.
Option.
Yes, correct. Now let's go to the next question. So this is question 3. I hope it's too small. Let me zoom in so that you can see. Now what is asked? Determine the slope of the beam at point A shown below. E and I are given, and this is the loading. So it's a simple problem. Okay, so it's a very simple problem. So what is the procedure? First, we have to analyze the real beam. So let me not take the numerical values now. So it is a simply supported beam. Let us take the span as 2L. So here it's L, here it's L, and at the midspan we have a concentrated moment M. So could anyone tell quickly, based on your experience, what will be the reactions at A and P? Can also do this and find out the reactions at A. So what does that result in? Moments about B, right? So M is a clockwise moment and minus reaction at A into 2L equal to 0. So we'll get RA as minus M by 2L, and there's no vertical force, which means RB is M by 2L. So the reactions are like this. Here you have M by 2L. Here you have M by 2L upwards. And you have a midspan concentrated moment of M. What is the next step? So we have determined the support reaction. Then just draw the bending moment diagram. So the convention is, so the convention for bending moment diagram is sagging is positive, right? So that is important when we use the conjugate beam method. So for the left span, if you take a section at the middle, it creates a hogging moment. So left, it's like this. And on the right side, you have a sagging moment. So it's an upward reaction. So M by 2L acting at L. So it will be something like this. Okay, simple. So this is minus, this is plus, this is minus M by 2L into L. So M by 2, M by 2. So there's a jump of M, and that is what is given by this concentrated moment M. So everything is consistent. Now what is the next step? Consider the conjugate beam. What should we load the conjugate beam with? We should load it with the M by A diagram. And what are the boundary conditions? So this hinge support remains a hinge support. This also remains a hinge support. Why? Deflection is 0, means moment is 0. Rotation is shear force, which is non-zero. So the hinge support is this remains as it is. And what is the loading? Loading is like this. This side, so negative hogging moment means negative, which means the deflections are downwards. And sagging moment is positive, which means the deflections are upwards. Sorry, not the deflection, the load intensity. So this is M by 2EI. And this one is minus M by 2EI. So that's it. Let us find out. So what is that they're asking? They're asking the slope at the point A. So what is the slope at the point A in the real beam? So slope at the point A in the real beam is the same as the shear force at the point A in the conjugate beam. What is the shear force at the point A in the conjugate beam? That is nothing but the reaction. So we know the sign convention is like this. Left side upwards and right side downwards is positive. So reaction is expected to be upwards. That case we get the theta at the point A in the real beam, which is the shear force in the conjugate beam at the point A. Now how to compute the shear force? Shear force is nothing but the reaction. So better let's find out the reaction. So for finding the reaction, you can always replace the loading system by a statically equivalent system. So what is a statically equivalent system for this? So this is a triangular load distribution. What is the total force? It is half into basis L into height M by 2EI. Since it is minus, I have drawn it downwards. And where does this act? It acts at 2L by 3 from this side. And here what do we have? Same magnitude acting at 2L by 3 from this side. So this is ML by 4EI. And here we have the VA, and here we have VB. Now we are interested in finding a V bar A and V bar B. Now we want to find V bar A. So let us take moments about point B, set them equal to 0. So what do we get? 2L by 3 minus, so it's minus clockwise minus 2L by 3 into ML by 4EI minus, no, not minus, this is plus counterclockwise, ML by 4EI into 2L minus 2L by 3 minus BA into 2L equal to 0. You do this, so just rearrange, you will get VA as yeah, so you will get VA as, let me, okay, let's do it. So this is 2 ML by 4EI into you get ML by 4EI, you can take commonly out. And this you take it to this side. So you get ML by 4EI into 2L minus 2L by 3. And you have another minus 2L by 3. So you get 2L by 3. So into 2L by 3. And there's a 2L coming downwards. This cancels, you get ML by this VA bar, ML by 12EA. So theta A is ML by 12EA. So what it is? M is 5. So sorry, not 5, 50. So it is 50 into 10 power 3. L is what? L is 4 by 12 into E is 200 into 10 power 9 into I is 8 into 10 power minus 6. So I get 50 into 4 is 200, 200 gets cancelled. And then you get 1 by 12 8s are 96. So that is approximately 0.01. Clear? Let's go to the next question. Again, it's the same beam, same load. What they are asking is the maximum displacement in the beam. Yeah, they're asking the maximum displacement in the beam. That's it. So we already know what the loading is. So what was it? Consider the conjugate beam. This was m by 2 EI. This was again m by 2 EI. M by 2 EI. These are the boundary conditions. Do you know where the maximum deflection will occur? We don't know, right? In general, for this beam, there is no symmetry or anything. So we can't say where the maximum displacement will occur. So we need to find the deflection as a function of x and then find out its maximum, which means we need to get the bending moment diagram for conjugate beam. Let's do it. It's not difficult. So we already have the loading. So yeah, so we already have the loading. But what do we know about the loading conditions? Okay, so we saw that the reaction, right? What was the reaction? The load is like this. And the reaction, so this is downwards. This is upwards. And here the reaction is we got, what did we get? We got a yeah, we got it as ml by 12 EI, which is positive. Yeah, so we got a positive reaction of ml by 12 EI on left side. And since the loading is anti-symmetric, so here it is ml by 12 EI, and here it is ml by 12 EI. And this is m by 2 EI minus m by 2 EI. So the loading is symmetric. If you consider the conjugate beam, the loading is symmetric. The support reactions are symmetric. Sorry, loading is anti-symmetric. So the loading is exactly anti-symmetric. That is so this is a plane of symmetry. Okay, this is what we call as a plane of symmetry. To this side, if you take a point x, and to this side, if you take a point at the distance x from here, if the deflection is v, here the deflection will be minus v, and the vice versa. So loading is antisymmetric, support reactions are antisymmetric. So we expect bending moment also antisymmetric. So it is sufficient to look at only half of the beam at once. So they're asking the maximum deflection, right? They're asking the maximum deflection. So if we look at one side and find out the maximum, the other side will be the negative of it. So the magnitude is not going to change. So let us solve for it. Let us find the expression for bending moment in this. Okay. So there's a linearly triangular loading. Let me take the origin at this point and consider this as x. Okay. Now let us consider this portion of the beam. It is of distance x. Here I have ml by 12 EI. Here there is an internal bending moment m bar. So what is m bar? Very simple. ml by 12 EI x minus, it's linearly increasing. So what is the maximum value? M by 2 EI x by L. So that is this value acting over x. We should take half of it and acting at a distance x by 3. So that is simple. So again, what do you get? You get ml by 12 EI into, so this is 3, 2 2s are 4, 4 3s are 12. So x minus x cube. So you can't take L commonly out. So if you take say L square commonly out, you get x by L minus x cube by L cube. So this is the bending moment, which is nothing but in the real beam, it is a deflection. So this is a positive constant. It's not going to change. It's a positive constant. This is the variable. So to maximize, you want to get maximum V, which occurs at maximum of this quantity. So that's it. How do you find maximum of it? You say d by dx of x by L minus x cube by L cube equal to 0. So what do you get? You'll get, if you take 1 by L commonly out, you'll get 1 minus 3 x square by L square equal to 0, which means x is equal to plus or minus L by root 3. Now substitute this in this one. Okay. So when you maximize it, you'll get 2, but this is an odd function. If you put x is equal to plus root 3 by plus L by root 3, you'll get some quantity. If you get x is equal to, if you put x is equal to minus L by root 3, since it is an odd function, you'll get exactly the negative of this. So so you can just take one of them, which is the maximum. So you understand what it is, right? So the positive occurs on one side and the negative occurs on the other side. But again, we know that x less than 0 is not allowed. There's no beam on this side. So you have to consider only the positive x equal to L by root 3 thing. Now, if you substitute that into this, you will get, what do you get? You will get m, the maximum deflection as, you will get V max as m L square by 12 EI into 2 by 3 root 3. Now, if you compute what it is, m as 50, L as those things, if you compute, you will get the this quantity as, you will get it as 0.016 meters. So which corresponds to 16 mm. So yeah, we have solved this. Yeah, so we have solved this. Let's go to the next question. Okay, let me pause here and take any questions if there are. We have solved 4 questions, 5 questions indeed. So are there any doubts? Can I clarify? If there are any doubts, I can clarify. Are there any doubts?
No, sir.
Okay, thank you. Okay, now let's go to the 5th question. It is slightly more involved, but it's easy. It's still easy. So what is asked? Determine the deflection at the point B. So at this internal hinge, using conjugate beam method. So very simple. Let's start in the usual manner. So as usual, what is the first step? So this is a multi-span beam. It is statically determinate. So first step is to determine the support reactions. So split it into 3 parts. At D, what do you have? D is a free end. So at C, you have a VC plus, say VC on the right hand side, and you have VC minus, which is on the left hand side, and in between you have a support. So they are not in general equal. And this is a continuous. The beam is continuous over the intermediate support. So it will also transmit a moment MC. And I marked it purposefully in the wrong direction because physically we know that the moment has to be in this direction to resist this applied force. You have an MC here also, which is equal. This is an internal hinge. So you don't have moment there, but you have shear force. Let's call it VB. And it should be equal and opposite because it is an internal hinge without any external loading. And here you have VA, MA. And all are subjected to the same forces. Now, very quickly we can find out what are the unknowns. So quickly you can get VC plus is nothing but W into L. Let us take it's all 2 meters, right? So let us take each of them as each of the spans to be of length L. So VC plus is WL. And what is MC? MC is W L square by 2 in this direction. So it is hogging. This is upwards. And in this span, what do we see? We have, if you want to find VB, what should you do? Take moments about this point, okay? Take moments if you want to, you don't want to find VC minus really. Okay, so we only need the bending moment diagram. We don't need the shear force diagram for finding the conjugate beam loading. We need only the bending moment diagram. So let's find out what is VB. Okay, so VB, to find VB, take moments about C. In that case, you get minus VB into L plus WL square by 2. Right? Why that plus WL square by 2? Because WL acting at L by 2. And then what else? You also have the moment at the point C itself, which is in the clockwise direction. So minus MC equal to 0. But MC itself is WL square by 2. So these two is cancel each other, which implies VB is 0. Therefore, it means that this part of the beam is not at all interacting with this. So there is neither a shear force nor a moment that is transferred. So this is equal to 0. So nothing is transferred from this side to this side. So they said it is just the usual cantilever. So which means MA is WL square by 2 hogging and VA is WL upwards. Now let us draw the bending moment diagram for this beam. So it is nothing. Here it is like this. And here it again goes to 0. And everywhere we have here there's an internal hinge. So it is 0. Here we have an intermediate support, so it is maximum. And here it has the same value of WL square by 2. So the maximum values are WL square by 2. Now let us consider the conjugate beam. Okay. So the fixed end will become free end. So this is the bending moment diagram. If you consider the conjugate beam, you have to add an EI, bending moment diagram by EI. So this is the point A, this is the point B, this is the point C, and this is the point D. So the and all the bending moment is negative everywhere. So all the loading is downwards. At D, what do we, so A is a fixed end, which means BA is theta A is 0, which means on the bending, on the conjugate beam, so it's a free end. At B, we have an internal hinge, so it will become an intermediate support, right? We saw why it is so. At C, we have an intermediate support that will become an internal hinge. And at D, we have a free end, which means the deflections and slope are non-zero. If they are non-zero, it means the bending moment and shear force should be non-zero on the conjugate. So this becomes a fixed end. What are they asking? They're asking the deflection of the point B. That is this. So deflection of the point B in the real, not D, theta. Deflection of the point B in the real beam is equal to the bending moment of the point B in the conjugate beam. So it's very simple. What is the bending moment of the point B in the conjugate beam? Just this, right? So it's integral. So if you so again, it's simple. Take a small strip. How much force it has? It has W dx. So it is integral df into x. So it is nothing but this W is different from that W. Say call it Q or something. It is Q dx into x. But what is Q in this span? If I put the origin here, let me put the origin here. If I go, this is nothing but Q is nothing but W x square by 2 EI. So if you put x equal to L, you will get W x square by 2 EI. Into x into dx. So just finish it. So x cube, if you integrate, you'll get x power 4 by 4. So the answer is, and you have to integrate from 0 to L. The answer is W L power 4 by 8 EI. Is it plus or minus? It is minus, right? It is minus. So just plug in the numerical values. W is 20, L is 2. So 2 power 4 is 16. 16 into 20, 16 by 8 is 2. 2 into 20 is 40. So the answer is 40 by ES. Go to the next question. So this is a discontinuous beam. The properties, the material properties of the beam are discontinuous. So what we have is, we have the usual beam, but for one half of the beam, it is thicker with moment of inertia 2I, and the other half is of moment of inertia I. In the middle, we have a point load and a moment. And it is supported in the usual fashion, simply supported. So let us get the support reactions. Now it's very simple. We have solved so many problems. How do you do it? Use principle of superposition. Consider one load at a time, and then just sum up the support reactions. Sorry, this is like this. Anyway, it doesn't matter. So consider one load at a time. L. In here you have an L and L, and moment M. This is P. So first one is very easy. So what are the support reactions like? P by 2. P by 2 plus this side, what do we have? We did in the first problem, right? M by 2L. M by 2L. M. Straightforward. We'll draw the bending moment diagram. So P by 2 acting at L. So it is P by 2 acting at L plus the other bending moment diagram is like this. So Left side it is hogging. So minus m by 2l acting at L. So it is minus m by 2. Here it is n by 2. Add both. What do you get? So just to get the schematic right, moment is 5 kilonewton meter, right? So moment m is 5 kilonewton meters, and P into L is what? 40. 20 into 2 is 40 kilonewtons meter. So if you superpose these two, this will be much bigger than m. So this positive value, so this will never become negative. So PL is 40, m is 5. So 40 minus 5 is 35. So it will still remain positive. So the resulting bending moment diagram will be like this. If you superpose this, both are positives. So this value is PL by 2 minus m by 2. And this value is PL by 2 plus m by 2. That's it. And this is L and L. This is L. This is L. Done. So we have got the bending moment diagram. But in this case, we should be careful that you cannot simply divide it by EI. Left hand side you have 2I and the right hand side you have I. So if you do that, the bending moment, the loading onto the, again, let us determine the boundary conditions. Okay. So it is the same. Hinge support remains a hinge support. So if you consider the conjugate beam, it looks like this. Here we have PL minus m by 2 divided by 2EI, right? So this will be further reduced. And this side we have PL plus m by 2 divided by EI. So it is much bigger. It's like this. And both the moments are positive. So the loading is upwards. So what is this height? It is PL minus m by 2 EI. So by 4 EI. And what is this height? It is PL plus m by 2 EI. Now what are they asking? They're asking for the deflection and the slope at the point B. So at the point B is at the middle. So they're asking the deflection and slope at this point. For that, as usual, we need to determine the support reactions. Again, for finding the support reactions, you can replace it with a statically equivalent load system. So what is the statically equivalent load system? What is the total force that acts here? It is PL minus m by 4 EI, which is the total, which is the maximum, which is the height, base is L, and triangle area is L by 2. And here the maximum force is PL plus m by 2 EI, and triangle area you'll get L by 2. What else? We need to find the distance at which these are acting. So this distance is 2L by 3. This distance is 2L by 3. Now finding the reactions is very simple. So what are the reactions? Take moment. So sigma moment about the point C equal to 0. This is point A, C, and point B. You do that, what do we get? The shear force at the point A acting at 2L will produce a counterclockwise moment minus PL minus m by 4 EI into L by 2 acting at about C, right? It acts at 2L minus 2L by 3. and the other load is PL plus M by 2EI. Area is this, acting at 2L by 3 equal to 0. So what do we get? We get VA as, if you do all this rearrangement, let me write down the final answer. Yes, you will get VA as minus PL square by 6EI. You see, it doesn't depend on M in this special case. Why? It's because this will be M by 8. So here you will get a 4L by 3. So 4 gets cancelled. You'll get an ML square by 8EI, ML square by 4EI, and not 4, ML square by 12EI. And here you also have another ML square by, wait. So 2L by 3 minus 2L by 3, you will get 4L by 3, and 4 gets cancelled. You'll get ML square by 6EI, which is positive. And here you have ML square by, so 2 gets cancelled, 6EI negative. So those two gets cancelled, and what remains is PL square by PL cube by 6, PL cube by 3EI, and when this 2L comes this side, you get PL square by 6EI. So this is the shear force at point A. But what we want is, we want to get theta B. So this is shear force in the conjugate beam at point A, but we want theta B. So theta B is nothing but the reaction. No need. Let me draw it again. Okay. So if we take this span AB, what are the forces? You have the shear force at point A. You have this, which is of this much magnitude, that PL minus M by 4EI into L by 2. And you have the internal shear force, PB, and the internal bending moment, MB. Now what is VB? It is just sum of these two. So if you add these two, what do you get? You will get PL square by 8EI minus PL square by 6EI, which is nothing but PL square by 12EI. Sorry, PL square by 24EI. And you'll have this minus ML square by 8EI. So you'll get VB as minus PL square by 12EI minus ML by 8EI. So if you just compute this turns out to be, so just if you plug in the values, you will get this as you'll get 13.75 by 3. So this will come out to something like 4. Let me find out. It is 13.75 by 3. 4.583 by EA. So that will be the slope at the point B. Now, if you find same thing, now if you want to find MB bar, what you should do? So MB bar is counterclockwise, plus these two will give a negative moment. So plus is actually minus VE bar acting at L minus PL minus M by 4EI. PL square minus ML by 4EI. Where does it act? It acts at L by 3. Set it equal to 0. Okay. This acts at L by 3. It's a triangle, so it acts at L by 3. This is L by 3. If you solve this for MB bar, which is nothing but VB, you will get that is equal to P. So here you have a, this is minus, right? Here you have a minus, and this is also minus. Minus PL cube by 8EI minus ML square by 24EI. So if you again plug in the values, you will get it is equal to you'll get it as, so PL cube by 8EI will be P is what, 20, L cube is 8, again 2 into cube is 8, so you'll get 20 by EI. And minus what is M? 5. L square is what? L square is 4. So you'll get M by 6EI. So 5 by 6EI. This is nothing but minus 20 minus 2.5 by 3EI. This is nothing but minus. So take LCM, you'll get minus 62.5 by EI. So it means the deflection is downwards. The deflection at point B is downwards, and the rotation at point B is clockwise. So if you see what are they? 62.5 and 13.75. So B is the answer. If you can't see, let me see. So the correct answer is B. Let's go to the next question. So yeah, let's go to this question. So this is another simple question. Instead of a beam, now we have a frame. So we have two beams connected like this, and we are asked to use the method of virtual work. Okay. So here we'll use the unit load method. We'll use the unit load method. So what do we need? The bending moment in the real virtual and the bending moment in the real system. So, okay, I didn't say what they're asking. They're asking the horizontal deflection of point C. So we are asked to find out the horizontal displacement of the point C. So what is the real system? Let us solve the real system first. As usual, first step always is to draw the free body diagram. So isolate the members as we do it for trusses. This is A, B, B, C. At C, we have a concentrated moment of 1 unit, 1 kilonewton meters. And there is no other force coming onto this. At B, we can have. Yeah, right. So at B, you can have. So this is a free end. So there is no other unknown force that is acting here. At B, you can have a force like this. They call it Bx. Force like this, By. And a moment, Mb. But if you draw the free body diagram for this and write down the equilibrium equations, there is no vertical force, which means By is 0, Bx is 0, there's no horizontal force, and Mb you will get it as -1. So it is hogging. So here it is hogging. So reverse the sign here. At B, since it is a connected joint, exactly the same resultants will be transmitted here. So here you have 1 kilonewton meters hogging, and this end is cantilevered with a uniformly distributed loads. Now finding the support reaction is not very difficult. What is the total vertical force? It is 0.4 into 10. So the support reaction is 4 kilonewtons. And what is the moment that comes here? It is 1. Okay, so that will be hogging, of course. What will this moment be equal to? It will be 1 plus 0.4 into 10 is the total force. And where does that act? It acts at 5. So 40 into 5, it is 21. Yeah, so we have determined the moments at the ends. Now we can directly draw the bending moment diagram for this. So this is under a case of pure bending. Okay, so we usually draw the moment on the tension side, sorry, on the compression side. So bottom is under compression. This is minus 1 kilonewton meters. And here what do we have? Here it starts at 1 and ends at 21. And there is a uniformly distributed load, which means the variation will be quadratic. So here you have minus 1 kilonewton meters. Here you have minus 21 kilonewton meters. And this length is how much? 10. And this length is how much? 8. This is 10 meters. And this length is 8 meters. So this is the real M. So let me do one thing. Let me set up two coordinate systems. Since there are two beams, for this beam, I'm taking the origin here. And let me call this x1. And for this beam, let me take the origin here. And let me call this as x2. Okay, it'll be helpful when we do the integration. So this is real system. Now, what is a virtual system? We want the horizontal displacement at the point C. So let us subject it to a horizontal force of 1 kilonewton. So the virtual system is something like this. Applying 1 kilonewtons here. And the rest is as it is. There is no load. Okay, the virtual is virtual. Now, as usual, if you draw the free body diagram, you have 1 kilonewtons here, which means an equal and opposite force of 1 kilonewton will act here. But this results in an unbalanced moment of 1 into 8, right? 1 kilonewton acting at a lever arm of 8 meters. So to counteract this, there will be a sagging moment of 8 kilonewtons meter. Will there be any vertical force? No. So the same forces will get transmitted here, which means you will have 1 kilonewton here. And there will be a sagging moment of 8 kilonewton meters. No vertical force, which means here the moment, if you take the equilibrium, it will just counteract, it will be 8 kilonewton meters, and there will be a tensile reaction of 1 kilonewtons. Will there be any vertical force? No. So that's it. Since there are no intermediate forces, this is the virtual bending moment diagram. What does it look like? This is sagging, compression is outside. So, and it starts at 0 because it's a free end. There's only a force that we have applied, and it ends at 1. Sorry, not 1, 8. So this is 8 kilonewton meters. And what do we have here? Same thing continues. And there are no vertical forces. There is no shear force. Shear force is 0 throughout the beam. So the bending moment diagram will be flat. 8 kilonewtons meter. So this is the virtual bending moment diagram. Okay. Now what is the unit load method formula? Principle of virtual work. The work done by the unit virtual load on the real displacements delta is equal to integral m of x, which is the virtual internal forces acting on the real internal rotations. So this is virtual This is real. But there are two beams, okay? So you need to do this for each beam separately. So in this case, that's why I took two coordinate systems, okay? This is x2 and this is x1. Same thing has to be replicated here as well. So here, let me take this distance as x2 and this as x1. Now let us find out the functional forms of these bending moments. So the real bending moment, what is capital M of x1? It is constant, it is -1. And what is capital M of x2? Is -1 minus wx square by 2, which is minus 0.4 x square by 2. Here it is simple. So what is small m of x1? It is 0 here and it is 8 at 8. So it is nothing but x1. And what is small m of x2? It is a constant which is 8 kilonewton meter. Now let us find out the work done. Okay, so it is nothing but in this case it is for this one. Okay, for this member it goes from x1 equal to 0 to x1 equal to 8. And what is the virtual bending moment? Virtual bending moment is x1. What is the real rotation? It is m by ei. And what is capital M? In this member, it is just -1. So this one multiplied by -1 by ei dx1 plus the other member x2 going from 0 to x2 going to L. What is the real virtual bending moment? It is constant 8. What is 10? L is 10 meters. So it is a constant 8. And what is the virtual bend? Real rotation? It is m by ei, where m is given by this expression. So it is -1 minus 0.2 x square by ei. This is x2 dx2. So it's a very simple integration. Integrate this, you'll get x1 square by 2. So x1 square is x1 square. Substitute the limits, you'll get 36, right? 8 into I'll get 36 by ei. Sorry, not 36. Gee. X1 square is 8 square, 64. 64 by 2 is 32. 32 by 2 ei. And here the first term is nothing but dx2, integral of dx2 is just 10. So 80. And there's a minus sign. Minus 80 by ei minus, so 0.2 x square. X square, if you integrate, you'll get x cubed by 3. So you'll get 0.2 into, so it is 200. 0.2 into x square, x cube, right? So 0.2 into 1000 is 200 by 3. So if you compute what this value is, so you get 32 plus 80 is 112 plus 200 by 3. Not 200, 200 multiplied by 8. So here you have 1600. So you get 1936 by 3. So it is option D. So yes, now we have the last two questions for the day. We already did 10, so we'll do 9 and 8. Let's do 8. Simple. We are given a linearly increasing loading. We are asked to find out the deflection of the point A using the unit load method. As usual, let us consider the real system. The real system. Let me call this as W of x given by, could anybody find out what it is? the functional form. Because we need to integrate, it's essential to know the functional form. That's why I'm saying this. So it is 25 over a distance of 10. So 25 into x by L. So it is nothing but 2.5x. Now let us draw the free body diagram, okay? So for each span, let me set up a coordinate system. Call this x1, call this x2. Okay. Okay, fine. So what are the reactions? Okay, so this portion, you can again, to find out the reaction, we can replace it with the statically equivalent system. What is the statically equivalent system? So this is say 2L, and let us take it as 5. This is a triangular load, so the total magnitude will be 25 into 10 by 2. So 250 by 2 is 125. 125 kilonewtons acting at 10 by 3. Right, L by 3. So 10 by 3 meters. So note that I have not taken it as 5 by 3. The triangle is throughout, so we should take 10 by 3. And we have the support reactions here. So it's easy to find out. So take moments about the point C. We get, if you take moments about the point C, you get 125 into 10 by 3 minus the reaction at B acting through 5 is equal to 0. You get the reaction at B as 125 into 2 by 3. So it is 250 by 3. And then what is the reaction at? So what is this? This is 2/3, which means what is the reaction at C? It is 125 minus this. So it is 125 minus 250 by 3. So this is 250 by 2 minus 250 by 3. So what it is? $125 by 3. Okay. Now let us draw the bending moment diagram. So in the span, let us call it the span AB. The span AB. What does it look like? So I have taken two coordinate systems. So if I take from here x1, it is hogging. So tensile side is downwards. So I'm plotting it this way. What is the functional form? If you cut at a distance x, the load that acts will be W into x. W into the load that acts will be Wx acting over a distance x. It will be, since it is triangular, you will need to take a half. And its centroid will be at x by 3 from the sectioning point. So it is W x1 cube by 6. The bending moment in this span. One, right? See, cut it at x. So this is x. Total force will be Wx. So this is actually it's not W, it is 2.5. 2.5. So it is total force will be 2.5. 2.5 x into the area of triangle x by 2. Where does it act? X by 3. So it is 2.5 x1 cube by 6. And in this span, what is the case? So in this span, let us take it this way. Okay, let us so the moment that comes onto the span will be 2.5 into L cube by 6, which is 2.5 into 5 cube by 6. So if you consider here, you will for the span, you're cutting at x by 2, x2. So if you cut here, or rather, let's not do this. You're cutting here, which is x2. There's a linearly distributed downward force. Right, there's a linearly distributed downward force. And what is the maximum value here? You need to take this x 2.5 into x2 plus 5, because this is also to be included. And there is an upward force of RB, right? RB is 250 by 3. There's an upward force of magnitude 250 by 3. So what is the bending moment in this span? M of x2 is nothing but minus 2.5 into x2 plus 5. Same thing. For the triangular load, this will be the bending moment, plus 250 by 3 into x2. Simple. So the real bending moment, how do you get it? So the real bending moment is, you're having it in two parts. M of x1 in span 1 is 2.5 x cube by 6. And in span 2 it is 2.5 x2 plus 5 the whole cube by 6, which is negative. This is also negative, plus 250 x2 by 3. So this is the real bending moment. Now let us find out the virtual bending moment. What are they asking? They're asking the displacement of point A. So what we need to do is we need to apply a unit force. So this is supported. Now this is an intermediate support. So yeah, so this is an intermediate support. Let us apply a unit load of 1 kilonewtons. What are the reactions? Very simple. Or directly draw the bending moment diagram. In this span, what it is this is 5 meters, right? So 1 kilonewton acting at 5 meters hogging. So this is minus 5 kilonewton meter at this point. And this side it is a hinged support, so it has to be 0. So that's it. There is bending moment is continuous since it's an intermediate support. So this is it. And how did we take the coordinate system? We took like this: x1, x2. So let us also write down small m of x. Small m of x1 is what? It is minus 1 x. That's it. At 5 meters, it is 5 kilonewton meters. What is m of x2? It is minus 5 plus x. Why? Now a plus x2. So if you take x2 is equal to 0, you get minus 5. And when you take x2 equal to 10, x2 equal to 5, you get 0. So this is the virtual bending moment diagram. Now, as usual, wait a minute. Something went wrong here. Yeah, it is minus 5 plus 6. I don't know why this scribbled like this. Okay, let it be. It is minus 1 x1 and minus 5 plus x2. Now let us apply the virtual work formula. 1 into delta of point A is equal to what? Integral x1 going from 0 to 5. What is the virtual bending moment there? x1 minus x1. x1 going from 0 to 5 minus x1. What is the real rotation there? Real rotation is this minus 2.5 x1 cube by 6. So real rotation is minus 2.5 x1 cube by 6 dx plus x2 going from 0 to 5. What is the real bending moment? Virtual bending moment, it is minus 5 plus x2. And what is the real bending moment? Real bending moment is this minus 2.5 by 6 x2 plus 5 the whole cube plus 250 x2 by 3. dx2. Okay, now it is simple. Let us solve this. We have, so the first integral is straightforward. We get minus into minus plus. So 2.5 x1 power 4 by 4. So it is nothing but 2.5 into 5 power 4 by, we get a 4. 4 into 6 is 24. Plus the second integral. Let us split it into two. One is minus 5. So, or wait, let us look at it as yeah, this can be done. So plus 0 to 5 minus 5 into minus 2.5 is 2 point. So the first part is 2.5 into 5, which is 12.5 by 6 x2 plus 5 the whole cube dx2. So that is the first term. The first term is this multiplying by this. Second term is this. So plus we get 0 to 5. 250 into 5. So it is minus 1250. So 25 fives are 125. Minus 1250 x2 by 3. And there's an EI everywhere. Okay, I have missed it, but mind it. And the third term is x2 multiplied by this. So the third term is x minus, so this is also minus integral 0 to 5 x2 multiplied by 2.5 x2 plus 5 the whole cube dx2. And the last term is plus into plus. (250) x2 square by 3 dx2. Now to this term, let me do a trick to simplify the integration. Let me add and subtract a 5. Okay. If I add, so there's already a minus, which means I'll get a plus. Okay. That's it. Now we can directly evaluate these integrals. So what is this? So this one, 12.5 by 6, and this is also 12.5 by 6. So it's 2 times. So we get 25 by 6, x2 plus 5 the whole cube. So if you integrate this, you'll get x2 plus 5 the whole power 4 by 4 within the limit 0 to 5. And if you integrate this, you will get minus 1250 by 3 x2 square by 2 within the limit 0 to 5. If you integrate this, we get this already power 4, so you get minus 2.5 by 6 x2 plus 5 the whole power 5 by 5. And if you integrate this, this we have already clubbed into this, so this need not be considered. Here you get 250 by 9 x2 cube within the limit 0 to 5. Let us evaluate all of them. We get so the first term is 2.5 into. So let me see what is the form of the solution. Two 2.5 into pi power 4 by 24. So the first term is 3125 by 48 EI. Second term is this one, right? You'll get this is positive. So 10 power 4 minus 5 power 4. So 10 power 4 minus 5 power 4 by 4 to 25 by 6. So this one is something like the next term is 125 by 1250 into 125 by 6. So that is also minus. That's minus of this. So that is get minus 78125 by 3. And look at this term, the fourth term. There you have x power 5. So you have minus. So you get 10 power 5 minus 5 power 5 divided by 5 into 2.5 by 6. So that's a minus 96875 by 12 EI. And the last term is 250 by 9 into 125. So and that is the plus. Finally, what do we get? What are they asking? They're asking the displacement of point A. Fine. So we get 3125 by 48 minus 9687. So 3125 by 48. 96875 by 12 plus 31250 by 9. Let us see. So this is 12.5 by 6. So this is okay. By 24, okay, this is fine. This one you get x cube, so x power 4, 12.5. So this is the first term. This is plus. Second term is this multiplied by this. So minus 5 into 1250. That is fine. Third term is this multiplied with this. So that is nothing but minus this. Minus 2.5 by 6. And we are adding another 5. So this becomes into 2. So it is 25. It is fine. This is 25. So this term we are dropping. And finally, we have x2 square by 3. So that is also okay. Yeah, I think it's right. So this is how you do it. You can check these numbers. I'm not sure these integrate these calculations you can check, but I'm sure the procedure is right. So let me go to the next problem and we'll see what we get for this. Uh, Let's go to the next one because it's important. It's a frame. So let me see this one. So using the unit load method, calculate the vertical deflection of the point D. So let's do it quickly. This is the structure. You're applying a uniformly distributed load here, which is 0.1 kilonewton per meter. So this is a free. This is free to roll. It doesn't have a vertical restraint. So the vertical reaction to this comes only at this point. So if you draw the free body diagram, at this point you'll have a vertical reaction of 0.1 into 10, which is 1 kilonewtons. And will it have any moment? No, it doesn't have any moment. So it will be 0. And here also we don't have any moment, but it can have a vertical reaction. But since there is no horizontal force as such applied on the member, it should be equal and opposite to this. So what is the total? What is the horizontal force that comes onto this? It is what is it? It is, so if we write moment equilibrium about the point A equal to 0, we get 0.1 clockwise acting at 5 meters minus RD acting at 8 meters equal to 0. So RD is nothing but 5 by 8. 5 by 8 kilonewtons. So this is 5 by 8 kilonewtons. So this doesn't have any shear force. So this is a 2-force member to 5 kilonewtons. It doesn't have any moment because this cannot resist any moment. This side, if you have a moment, it should have an equal and opposite, but this acts through the point, so this cannot have any moment. So the same force should be transmitted here. So this will also be 5 by 8 kilonewtons. And here, since there's no moment, the moment here is also 0. But about this point, there is no force acting on this member. So the internal horizontal force that comes on here is 5 by 8 kilonewtons. And the moment is how much? So there's a net counterclockwise moment of 5 by 8. To resist it, there will be a clockwise moment of 5 by 8 into 8, which is 5 kilonewtons meter. Equal and opposite moment will go here. This is also 5 kilonewtons meter. And this, so equal and opposite force, 5 kilonewtons. So this force should be 5 kilonewtons. And there cannot be any moment because it is pinned. So what is the real bending moment diagram? We got it in one step. Starts from 0, increases to 5. It is sagging. As you can see, it is sagging. So compression side is outwards. So this is 5 kilonewton meters. Here, what do we have? It decreases to 0. 5 kilonewtons meter. This one, there's no bending moment. There's no bending moment, there's no shear force. So it is just what it is. Okay, so this is real. Now let me take the origin of the coordinate system, this side for this member and this side for this member. So what is capital M of x1? It is 5, right? So it is 5, which means it is just 0.5 x. 0.5 times x. M of x2 is also, M of x2 is 5 by 8 times x. Hope you get how we get this. So that is the real bending moment diagram. now let us get the virtual bending moment diagram. Now let us get the virtual bending moment diagram. So they are asking to find out the vertical deflection at the point B. So what is the virtual load we should consider? It's like this. How much? 1 kilonewtons. So what will come here? Again, draw the free body diagram. So 1 here, which means one by method of joints we are actually doing. So this should also be 1 kilonewtons. There's no horizontal. Yeah, so this reaction is also 1 kilonewtons because it's along the same line. If you take moment about this point, there is no other external force, which means the horizontal reactions are 0. There's no horizontal reaction. It acts like a kind of beam. So this is one, there's no horizontal force. But this one creates a counterclockwise moment of 1 into 10. So we have a clockwise moment of 10 kilonewtons meter. Equal and opposite moment will go here. Equal and opposite force will come here. So this is under a tension of 1 kilonewtons. This is under 10 kilonewton meter. 1 kilonewton. So there's no net force, net shear force, but there's a moment of 10 kilonewton meter. So this is sagging. So this will also have a moment of 10 kilonewtons meter. And force of 1 kilonewtons. So this is the free body diagram. We can draw the bending moment in one step. What it is. So if you take about this point, it is sagging. Right? So just a minute, there's a correction. This shouldn't be straight. Because it is quadratic, right? Since it is linearly, it's a uniformly distributed load. So this is quadratic and this is straight. So this is 0.5 into x squared by 2. So when you get to not 0.5, so the maximum is 5. So it is 0.1 into x squared by 2. Correct. Sorry for this mistake. It should be 0.1 into x squared by 2. But here it is straight because there is no distributed loading. It is straight. And what is the magnitude? The maximum is 10. And here it is under constant bending moment. Sagging, again 10 kilonewton meter. And here it is also sagging moment, positive 10 kilonewtons meter. So this is the real bending moments. And what are the real forces? Virtual bending moments. Virtual bending moments are m of x1. So I'm taking x1 from here. X2, where did I take? X2 I'm taking from bottom, right? So X2 I'm taking from here. And X3 I can take, but it doesn't matter because it will be anyway multiplying with 0, right? Nevertheless, yeah. I can put an X3 from here and write this as capital M of X3 equal to 0. But that doesn't matter. Since it is multiplying with 0, it will not contribute to the deflection. So yeah, I can take X3 from here. What is M of X1? It's nothing but 1. It is 1x. So M of X1 is X1. Small m of X2 is what? It is a constant 10 kilonewton meter. Small m of X3, it is X3 kilonewton meters. Now let's write down the principle of virtual work. So one acting at delta is equal to, so integral over x1 going from 0 to 10, and the second one integral over x2 going from 0 to 8, and the third one integral x3 going from 0 to 10. Yes. Now what is so this one is x1. What is the real rotation? 0.1 x square by 2 ei into 0.1 x square by 2 ei dx1. x1, x2. I hope I'm right. Yeah. And in the second thing, what is the real virtual bending moment is 10. Real bending moment is 5 by 8 x2 dx2. Third one, the virtual bending moment is x3. Real rotation is 0 by ei to dx3. So this is by ei. This is not going to contribute. We don't need that. We'll only consider these two terms. So what are they? It is a very simple integral. So we get 0.1 x1 power 4. Here there's a by 2 ei by 4 in the limit 0 to 10 plus 50 by 8 x2 square by 2 within the limit 0 to 8. So let's compute these. X1, so 10 power 4 by 4 into 0.1 by 2 plus 50 into 8 square by 16. Let us check. So the answer is okay. Sorry, there's a mistake here. So there is a 1 kilonewton that I have missed out. So the shear force here is not 0, right? So this. So the correct expression is, if you draw the free body diagram here, you have 1 kilonewton at a distance x, and you have this. So it is actually 1 x minus 0.1 x square by 2. So it's like this. Now if you get, you will see it is 10 minus 0.1 into 10 square by 2. So 0.1 into 100 by 2, 10 by 2 is 5. It is 5. So this is incorrect. So this is a minus and there is a plus x1. So here we have, this is a minus and there's a plus 1x by ei dx1. So this is a minus and there's a plus. So if you substitute the values, you get 1225. This is in kilonewtons meter square. So it is kilonewtons meter. So it is into 10 power 3 divided by 3 into E is 200 into 10 power 9 and I is 8.33 into 10 power minus 6 into I is 8.33 into 10 power minus 6. So the answer we get is 1225 divided by 3 into 200 into 5 by 8. 2 by 8. The answer is 0.245 meter, which is 245 mm. So it is this option B. And 10 we have already seen. So yeah, I hope this was a useful session for you. Again, I'm over time by too much. I'm over time by 50 minutes. Sorry about it. I got this question took some time. But yeah, next time I'll make sure these issues don't happen. Kindly let me know if there are any doubts. You can ask in the discussion forum. And so shall we close this session?
Yes, sir.
Okay. Thank you for attending. Let me stop sharing the screen and I'll stop recording.